Dear students, I hope everybody is doing well and enjoyed the sessions of our electromagnetic field theory, which were taught using these natural examples. Like that, I am going to drill the concepts of these electronic devices and circuits in a simple way with the natural examples, because electronic devices and circuits is the most important subject to understand the fundamentals of our electrons and communications. If you are having a grip on this subject, you can understand all other communication subjects also very well. So that's the reason I would like to ask you to concentrate on these lectures in a sequential way, so that can be helpful for attempting your competitive examinations like GATE and IES also. So now in this class we are going to see the classifications of materials. And before going for this classification of materials, let me recollect the concept of our nature of the atom. So everybody knows from your intermediate, Rutherford has given an atomic model in 1911, and he concluded that atom consists of a central particle which is heavy particle having a positive charge which can be called as a nucleus. So this is called a nucleus. Around it, the electrons are orbiting and which are having the negatively charged like this. So these electrons are having a negative charge, the nucleus is having a positive charge. As soon as you are telling nucleus is having a positive charge and electrons are having a negative charge, definitely there will be a force of attraction between these two charges as per the Coulomb's law. So the central heavy particle nucleus, which is always attracting the electrons towards it, because opposite charges attract each other, and same charges repel each other also. But here they are opposite charges and electrons are having a negatively charged, and whose charge is 1.602 into 10 to the power of minus 19 coulombs. But whereas the particles inside the nucleus, which are nothing but the protons, having the positive charge. Once they are having opposite charges, they can attract each other. But if they are really attracting like this, all the electrons will fall into the nucleus. But it is not happening. Electrons are actually not at all coming to this nucleus directly. If they are actually fell into this nucleus, the atom will be collapsed. But I am telling you, my dear friends, atom is existing. Atom is existing means there is always a force of attraction between this electron and this proton, but it is not coming to the nucleus because electrons are maintaining always a kinetic energy by revolving into this. So that is the reason immediately I can say that electrons are not stationary. Electrons are moving in these orbits like this with some velocity which is having some kinetic energy. So from your physics, what is the kinetic energy of the electron here? The kinetic energy of this electron is half into mv square. This is the energy that is positioned by the electron because of the movement around this nucleus. But whereas if you know this gravitational force expression, that means the force of attraction between this nucleus and this one, and you know very well from your Coulomb's law, that is nothing but the force existing is F is equal to Q1 into Q2 divided by 4 pi epsilon naught into R square. This is nothing but the force that is existing between these two opposite charges. So here Q1 and Q2 are same, of course. Proton is having plus Q and electron is having minus Q. So Q into Q is nothing but Q square. So you can say that this is Q square by 4 pi epsilon naught into R square. This is the force that is existing between this proton and as well as electron. And this is actually attracting this towards its center, that is called centripetal. But this force is actually balanced by the kinetic energy of this electron. That's why I can say that the electrons are not actually moving to this nucleus because this kinetic energy is balancing this force of attraction. That's why if these two things are equal, I can say that if half mv square, which is nothing but the kinetic energy of the electron, is equal to your q square by 4 pi epsilon naught into r square, where r is nothing but the distance from this proton to this electron. This is nothing but the r. If both are equal means they are balancing with each other. That's why the electrons are not actually coming to this nucleus directly. They are actually revolving into this one. Very simple, my dear friends. The atom is existing because this kinetic energy is balancing this force of attraction that is existing between these two charges. I can tell you the best example. Suppose, for example, naturally, if I am riding a cycle here and the force of attraction is there, always will be there with the cycle. Suppose if the cycle is stationary, then definitely you can fall down. But as long as you are riding the cycle with some velocity, you are having always half mv square. So indirectly what you are doing? You are balancing the force of attraction by the earth with the velocity of the vehicle. So as long as you are in the dynamics, as long as you are in moving the cycle with some velocity, then definitely you can balance it. And whenever you are actually coming to the rest, definitely you can fall down, because there is always a gravitational force of attraction. Exactly similar to this. As long as the electrons are revolving around it, there is no problem at all, because they are always having some kinetic energy which is balancing the force of attraction between the positive and the negative. So this expression is given by Coulomb's. So Coulomb's law of attraction and this force is balanced by this kinetic energy what the electrons are actually maintaining here. That is the reason I can say the atom is existing, and this is the model given by our Rutherford in 1911. So from this I can say how many electrons are actually moving around this nucleus. That depends upon the atomic number. And you know very well how to write the electronic configuration of this, configuration of your elements. So it depends upon the atomic number, you can decide how many number of electrons will be in different orbits. So that's why I can say that if you are taking a nucleus once again, let me say this is the nucleus which is a centrally heavy particle having the positive charge. This is the positive charge, and electrons are actually revolving into this. So they may be revolving in different orbits like this, and this is the second orbit, and this may be the third orbit in different orbits. So from this discussion I can say the conclusion is electrons has to rotate, has to orbit around it. If they are moving, if they are not moving, then definitely the atom is not going to exist. So that's the reason I can say whenever you are having a nucleus heaviest particle positively charged, the negatively charged particles, which are nothing but the electrons, are always revolving around this nucleus in different types of orbits. So how many orbits may be existing here? That depends upon the atomic number. Suppose for example, let me give an example, silicon. So silicon atomic number is, I can say 14. 14 is the atomic number. So how to write down this electronic configuration? The electronic configuration is 1s2, 2s2, 2p6, and you can say 3s2, 3p2. So just by seeing this electronic configuration, what you can say? It is having 3 orbits here. What are the 3 orbits? This is the first orbit, and this is the second orbit, and this is the third orbit. First orbit is having 2 electrons, second orbit is having 8 electrons, and third orbit is having 4 electrons. You know, the number of electrons in each and every orbit is given by 2n square. That is the general formula you have used for calculating the number of electrons in the orbit. So that's why first orbit you are having 2, second orbit you are having 8, third orbit having your 4. So this particular silicon is having 3 orbits. Let me say this is the first orbit. So first orbit how many electrons? You can say that there are 2. This is the first and these are the second. And in the second orbit 8 electrons. Let me say this is 8. 1, 2, 3, 4, 5, 6, 7 and 8. And in the second last orbit, that is nothing but the third orbit, you are having 4. This is 1 and this is 2. Let me say this is 3 and this is nothing but the 4. So remember friends, this is the first orbit and this is the second orbit and this is nothing but the third orbit. 3 orbits are there. In the third orbit, you are having 4 electrons. Whatever the orbit that is the last orbit, it can be called as a valency orbit. I can say that this is called as valency orbit, or otherwise I can say valency band. I can say that this is. So, just for clarity, I would like to give you, for example, if you are taking this energy level diagrams, and you can say this is nothing but the first orbit, and this is the second orbit, and this one is the third orbit. This is the third orbit. Listen carefully here. This is the third orbit. This is the first orbit, and the second one, and this is the third orbit. And in my example, my dear friends, in my example, third orbit is nothing but the last orbit. Last orbit can be called as a valency orbit. And remember, whatever the electrons which are having in this valency orbit, means last orbit, is called as valency electrons. So these are nothing but the valency electrons which are existing in the last orbit. So in our example in silicon, we are having 3 orbits: first orbit, second orbit, and third orbit. And remember, and there will be always a higher energy levels are there, which is nothing but this is conduction band. This is conduction band. And you can say third orbit is nothing but the last orbit is called as this is valency band. So there are 2 things. One is valency band, other one is nothing but the conduction band. So now I would like to give you, what do you mean by band? Band means group of energy levels. Let me say, in the first orbit, how many electrons? 2 electrons. 2 electrons are not having the same energy. And you can say that the second orbit you are having 8 electrons. 8 electrons are not having the same energy levels. And if you take a solid, the solid may be having millions of atoms, millions of electrons in the first orbit, millions of electrons in the second orbit. All these electrons are not having the same energy level. It will be having different types of energies. That band of energies I can write down. A group of energy levels I can call it as a band. Valency band means the electrons which are existing in the last orbit, third orbit, that is called valency orbit, are having energy ranges from one value to other value. Band means it is nothing but just a group of energy levels like this. Third orbit or second orbit or first orbit, whatever it may be. Now, conduction band means I can say it is a higher energy level band. Higher energy level band. So, for example, I am telling you, suppose if you are having a central nucleus, I am giving an example here. This is nothing but the nucleus, okay, and this is the first orbit, and this is the second orbit, and this is the third orbit, and one more orbit is I can say fourth orbit. This is nothing but the fourth orbit. These are different types of orbits. Let me just compare with your educational system. And here it is, let me say that this is centrally particle, which is a heavy particle, which is having a positively charged particle nucleus, like a principal. And the first orbit means, let me say that this is the first year students, and the second year students, and the third year students, and this is nothing but the final year students. In first year, there may be thousands of students, but all students are not having the same energy levels. That means they will be having an energy from one value to other value. That's why I am defining a band of energies, group of energies. You are not going to expect the same energy, same knowledge for every student. Knowledge levels from one value to other value. I am grouping up all of them. That is the reason this is nothing but the first band. Band means group of energy levels. Second year students are having different energy. Doubtless they may be having very good knowledge compared to first year. But all second year students are not having same knowledge. They will be having a group of knowledge levels. So that is the reason this is the second one is a band, third one is the band, and fourth one is the band. But remember here, if you compare the energy level of this, the fourth band, which is nothing but the valency band. Valency band means last band. It is having more energy compared to others. So because they are at a greater distance compared to all others with respect to the nucleus. If you are taking the first year students, they are actually bound to the nucleus. They are actually attached to the nucleus. Their energy level is less. Second-year energy level is somewhat more. Third years are somewhat more. Final years are having very good energy levels. So that's why if you give a small amount of additional energy to them, they can be detached from this institution and they can go to the society, they can work like an employees. So that's why if you are taking this energy band diagram, this first orbit and second orbit and third band, these things are actually having the energy different levels like this. Valency band means the outermost orbit, in our example the final years. If you give some small amount of energy to them, then definitely they can jump from this valency band to conduction band. What do you mean by this conduction band? Conduction band means it is the higher level energy band, and where these people, where these carriers can be acting like a free electrons or free holes, free carriers. So the final year students, just by giving a small amount of energy for them, they are going to get the placements and they can enter into the market, they can act like a free carriers. Exactly, here the last band electrons, whenever I give a small amount of energy to this, they can jump from this valency band to conduction band and they can be acting like a carriers. Now, how much energy we have to give for them? Third group, third orbit, that means valency band. The last band is having the more energy level compared to the first band and second band, there is no doubt about it. But how much energy we have to give? That energy is nothing but the forbidden gap energy Eg that is existing between this and this. So the energy that is existing between this valency band and conduction band is called as energy gap. That is called forbidden energy. If you give more than this forbidden gap energy, then definitely the electrons can jump from valency band to conduction band. So what is the measurement of this electron forbidden gap energy? What is the unit of this? The unit of this energy gap in these atoms will be electron volts. You know very well, the unit of energy is nothing but the joule. Joule in sometimes it is a smaller unit, it is a mechanical unit. Sometimes it is the biggest unit. But whereas if you take the case of the energy levels in the atom, our electrons are having a tiny particle, they are tiny particles, very small amount of energies. If you want to measure the small amount of energies, then definitely there should be a proper unit for this. That proper unit is nothing but your electron volts. So now I would like to tell you how to define this electron volt also. So what do you mean by this electron volt? Electron volt is nothing but the unit of energy, and 1 electron volt is equal to the energy gained by an electron whenever it is falling through a potential of 1 volt. I think you understood this. Suppose if you take an electron, if the electron is falling through a potential of 1 volt means whenever it is traveling through a potential of 1 volt, whatever the energy that is gained by this electron is called as 1 electron volt. That means very simple, no need to by heart the definitions also, my dear friends. Electron volt means the energy gained by an electron whenever it travels through a potential of 1 volt. What is the charge of this one? Charge is 1.602 into 10 to the power of minus 19 is the charge of the electron. This electron has to move through a potential of 1 volt. That means this into 1 volt. That is nothing but your joules. So electron volt is equal to 1.608 into 10 to the power of minus 19 into 1. So that is equal to 1.602 into 10 to the power of minus 19 joules. Because Q into V will be given in the joules. This energy gap will be measured in terms of electron volts. So depending upon the magnitude of energy levels, magnitude of this forbidden gap energy, I can decide what material it is. And here I would like to tell you, suppose if the energy gap is not existing, I can say valency band and conduction band overlap with each other. That is called nothing but your conductors. If the energy gap is very far away, valency band here is, conduction band is here, much more energy we have to give. That is called an insulator. And if the gap is actually approximately equal to 1 electron volt, then that can be treated as your semiconductors. So I would like to tell you, my dear friends, your energy gap is going to decide the type of the material. So what are the topic I have chosen here? Classification of materials. Classification of materials will be done on the basis of the magnitude of the energy gap that is existing between the valency band and conduction band. Just now we have concluded that the materials will be classified on the basis of the energy gap that is existing between the valency band and conduction band. So once again I would like to tell you, if you are taking an atom, depends upon the atomic number, you are having different types of bands, and this may be the first orbit, and this may be the second orbit, and this one is the third orbit. Third orbit means, in my example I can say this is valency band. Valency band means outermost orbit, and this is the first and this is the second valency band. I told you there is a band which is at the higher energy level, which is called as conduction band. This is CB, conduction band. There is always an energy that is existing between the valency band and conduction band, and this is called as EZ. And this EZ will be measured in terms of your electron volts. What is electron volt? 1 electron volt is equal to 1.602 into 10 to the power of minus 19 into 1 volt. That means this is equal to 1.602 into 10 to the power of minus 19 joules. Electron volt means it is a unit of energy which is defined very easily. That means it is the energy gained by an electron whenever it travels through a potential of 1 volt. So electron volt is the appropriate unit for measuring the energy levels of these electrons in an atom. That is the reason we have chosen this. So once you know this electron volt's definition, depends upon the magnitude of this, I can divide all these materials into 3 categories. Number 1, if the energy gap EZ is equal to approximately equal to 6 electron volts, that means it is the biggest energy level. Much more difference is here between the valency band and conduction band. If EZ is approximately equal to 6 electron volts means lot of gap is existing between the valency band and conduction band. That can be called as a insulator. It is an insulator which does not accept the flow of electricity. That means it is not going to conduct at the room temperature or at high temperatures also. So that because the gap is much more between the valency band and conduction band. So this is called as insulator. This material is called as insulator. Suppose if EZ is equal to approximately 1 electron volt, means very less. Both are actually almost all close to each other. Then I can say that this is semiconductors. Semiconductors. Semiconductors are the materials whose conductivity lies between your insulator and as well as conductors. So come on, if EZ is almost approximately equal to 0, that means no gap is existing in between. Your valency band and conduction band overlap with each other. There is no gap at all. Then at room temperature itself they are the conductors. So this material can be called as conductors. There are 3 materials, friends. Depends upon the energy that is existing between the valency band and conduction band. I am telling 3 materials: insulators, semiconductors and conductors. So in conductors what happens? Valency band and conduction band overlap with each other. A small gap is existing between valency band and conduction band means semiconductors. And a large gap is existing between valency band and conduction band means insulator. So that's why if you want to define different types of materials, you should know how much energy gap is existing between your valency band and conduction band. Now coming to the definitions, I can say insulator means it is a material which is not accepting the conductivity even at high temperatures because the energy gap is more. That means if you are giving much more energy to this valency band carriers also, they are not going to jump to this conduction band because much more gap is existing. Very simple. I am at this place. That floor is almost all 12 feet from this. Can I jump from this to this? No. Because the distance is very high. So that is the reason I cannot come to that level unless otherwise much more energy is given to me. But giving that energy is not a joke. So that is the reason your insulator, if you are giving more energy, more temperature to this, number of carriers may migrate from this to this, but less number of carriers may go to this. And if you are giving much more energy for this, the ultimate thing is it is going to be destroyed. It is nothing but the breakdown of the insulator. So that's why insulator is not a conductor. It does not conduct even at high temperatures also. If you are by compulsion, if you are giving the temperature, it is going to be destroyed. So like that, if you are taking the semiconductors, the name itself is telling semiconductors means partial conductors. They are not good conductors, they are not the insulators. Its conductivity lies in between insulator and conductors. Its conductivity lies in between conductors and insulators. Or otherwise I can say semiconductors are the materials whose resistivity lies in between conductors and insulators. And semiconductors are conducts very small at room temperature. For example, if you take your conductors, E is equal to 0. The energy gap is not existing. That means you can say valency band and conduction band overlap with each other. They are going to overlap. No energy is required. Even at room temperature also it conducts. For example, if you take a conductor copper or silver, whatever it may be, silver or copper, if you take this, then even at room temperature also they are going to conduct. For example, if you take iron rod, put on the stove, at room temperature itself, they are going to conduct. It is going to conduct. And even at room temperature also it is going to absorb all the temperatures here, means it is going to conduct. But whereas semiconductors may conduct at room temperature, but its conduction is negligible. So if you give temperature to this, then they are going to conduct very well. But insulators, if you give much more energy for them also, they are not going to conduct. So very simple to say, my dear friends, whatever the energy gap that is existing in between this valency band and conduction band is going to decide the type of the materials. So coming for this insulators, can I give an example? Example means you can say carbon, or otherwise you can say graphite. All these materials are nothing but these are the examples. I can say carbon or something like graphite or something. First listen to the discussion. Then at the end I would like to compare all these materials in a single sheet so they can understand very easily. Semiconductor means very simple. Semiconductors means they conduct off. So the best examples are germanium and silicon. And the conductor means you can say copper and silver. So writing the electronic configuration of the semiconductors, what is the atomic number of germanium? Germanium means 32 and silicon 14. So write down this electronic configuration. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2, 4p2. So if you calculate 4 plus 10, 12, 18 and 28, 30, 32. So like that silicon 1s2, 2s2, 2p6, 3s2, 3p2. So friends, observe in the last orbit. What is the last orbit here? Here the last orbit is 4th orbit. Here the last orbit is 3rd orbit. In the last and final orbit, totally here it is 4. 2 plus 2, here it is also 4. That means in the valency orbit, in the last orbit you are having 4 valency electrons. It is not 8, it is exactly off. So that's why if you want to have a stability or inert structure, your orbit should have 8 electrons. But if you compare with this 8, 4 is nothing but exactly off. So it is not a good conductor, it is not a good insulator. That's why these are called as semiconductors. The valence electrons will be 4, exactly off of the requirement. That is the reason they are semiconductors. For coming for these conductors, for example, if you are taking a copper means you can say that this is 29. So if you are taking this copper, I can say 1s2, 2s2, 2p6, and 3s2, 3p6, 3d10, and you can say 4s1. That means in the last orbit, how many electrons? Only one electron. So for conductors, always the valency electrons will be less than 4. So that's why copper is a good conductor. It will be less than 4. It is exactly equal to 4. And if you are taking insulators, definitely you can prove it is more than 4 like this. So depends upon the number of valence electrons in the valency band, I can decide what type of material it is. So I am telling you, my dear friends, depends upon the energy gap that is existing between the valency band and conduction band, you can decide which material it is. And using the electronic configuration also, you can decide the number of electrons in the valency band. And depends upon the number of electrons that are available in the valency band, you are deciding that whether it is a insulator or semiconductors or conductors. And one more thing is, coming for the temperature coefficient of resistance. In conductors, if you increase the temperature, the resistance also increases. That is called positive temperature coefficient of resistance. But whereas in your semiconductors, if you are increasing the temperature of the sample, the resistance decreases. It is called negative temperature coefficient of resistance. And of course, the insulators are not going to respond for the conductivity. They are not going to conduct even at the high temperatures. And the porcelain or otherwise mica or otherwise graphite, carbon, all these things are nothing but the examples of this. So I hope you understood the classifications of materials based on this energy gap as well as the number of valence electrons that are existing in the valency band. So within a single shot, I would like to give the total summary of this. Okay. Now let us have a look on this table. And serial number, the parameter what I am comparing for this. The classifications of materials are nothing but conductors, semiconductors and insulators. Coming for the first one, energy band diagram. Here, the valency band and conduction band overlap each other. There is no energy gap that is existing in between. That's why these conductors are conducting even at room temperature. And if you are giving the maximum temperature to this, if you are raising the temperature to the conductor, the resistance also increases, which is nothing but the positive temperature coefficient of resistance. And the example for these conductors are copper and silver having the valence electrons less than 4. So coming for the semiconductors, observe carefully. Here the valency band and conduction band are differentiated by an energy difference of 1 electron volt. That means if the energy gap is approximately equal to 1 electron volt, it comes under the category of semiconductors. What is semiconductor? Semiconductor means whose conductivity is in between conductors and insulators. What about the temperature coefficient of resistance? If the temperature raises, the resistance decreases because the conductivity will be more at the high temperatures. So that's why it is having negative temperature coefficient of resistance. The most famous materials are germanium and silicon. And already I have shown you the electronic configuration for this. And from this electronic configuration, you understood very clearly the valency electrons are nothing but 4. As it is 4, as it is exactly half of 8, I can say it is semi, means half. That's why they are called as semiconductors. Coming for the insulators, and the energy gap is very much high. It is approximately equal to 6 electron volts, which are existing like in your diamond, graphite or carbon or whatever it may be. As the energy gap is much more here, it is not so easy to jump the carriers from here, this valency band to conduction band. Valency band to conduction band. And that is the reason no conductivity is there. You may not expect the conductivity from this. And the valence electrons should be greater than 4. And example I told you, it is a diamond. So, if you are taking these material classifications here, you have seen what is a conductor, what is a semiconductor and what is an insulator. So, from this point onwards, my requirement is and my interest is only the semiconductors, because semiconductors are the materials which are very much useful for our electronic devices and circuits. Out of all these materials, our requirement is only semiconductors. Already you might have seen the examples of the insulators and applications also. And whereas for conductors also we have seen, if you are taking a wire or something like it is nothing but a conductor, and insulators are nothing but your ceramic materials and all these things which are used in your power systems. But our interest is to develop the electronic devices which are so fast and having very good applications. That is the reason I would like to select the materials germanium and silicon. So that's why in the next class my focus should be on the semiconductors, and we are going to discuss the types of the semiconductors in the next class. Okay, I hope you understood this lecture. Thank you.